Hi, welcome to Modern Optimization Methods. In this part, we will introduce the second part of Chapter 4, the algorithms for trust region method. In this part, we will introduce the outline of the algorithm as well as the KKT condition for subproblem. Finally, we discuss the radius for subproblem. Now, let's first recall the trust region radius delta. Recall that in trust region methods, the trust region radius is very important in the sense that if it is too small, then we cannot walk too fast. And if it's too large, then there may be some problems in approximating the model function. Therefore, we need to choose this trust region radius properly. So how do we choose it in an efficient way? So we need some measurement. Now in this part, we actually introduce that we use the agreement between the model function as well as the original function. So how do we measure the agreement? We use the following ratio here. We define this as a rho k. So rho k is a ratio of two parts. The numerator, if we take a look at the numerator here, it is actually the difference of the objective function at current iteration and the future iteration. And if we take a look at the denominator here, it is actually the difference of model functions at current iteration and the future iteration. Okay? So if the two terms match very well, then we can regard that this match is very good. In other words, there is a good agreement between the model function and the original function f. However, if there is not good agreement in the two terms, then this rho k will be in other ranges. Okay? So we will discuss this in the following details. Now, remember that this mk0 actually the same one as function f at xk. So, and mkpk is actually the optimal solution of model function within the trust region. Therefore, the difference of the denominator here is actually non-negative one. In other words, we got the denominator to be positive. Then let's look at the numerator. Okay, so we discussed different cases of this rho. Let's see the first case. If this rho k is smaller than 0, so rho k is negative actually implies that the numerator is negative, right? So in other words, the function value in the next iteration is greater than the current one. So remember that we are trying to look for the minimizer of function f. So we cannot allow this function value to be increased, right? So in this case, it means that the model function cannot provide us a reliable solution. Or in other words, the step length must be shrink. So we have to shrink the radius of the trust region and we repeat the process. Then we take a look at the second case, rho k approximately to 1. In this case, it means that the numerator and the denominator, they are comparable. In other words, there is a good agreement between model function and the original f. In this case, we can fairly expand a little bit of the trust region. Okay, so we enlarge the trust region radius. So the third case is that if we have this rho k close to 0 and it is positive 1 but far from 1, all right? So in this case, it means that we get some agreement of the model function and the original function. However, the performance is not that good. It is fairly good. Okay? So in this case, we just keep the current trust region and we move on. The final case actually means that if you get a very bad situation, for example, rho k is closely to 0 or not even negative, then we will shrink the trust region and repeat the process. So from this page, we can see that this agreement of the model function and the original function is very important. It actually provides us more information about whether we will enlarge the trust region radius or we will shrink the trust region radius. Now, based on the above measurement, we can present the trust region algorithm. So the algorithm runs in the following way. In the initial point, we must initialize the upper bound of trust region radius, delta hat. And we need to specify a starting trust region radius, delta 0, between 0 and delta hat. After that, we need to specify a parameter eta between 0 and a quarter. Then our algorithm starts. So we obtain the search step pk by approximately solving the subproblem. After we get pk, then we can calculate the rho k by our formula. This rho k actually, as we mentioned in the previous page, it shows the agreement of model function and the original function. So based on different cases of rho k, we can update the trust region in the following way. If rho k is smaller than a quarter, then we shrink the step size by a quarter. And if rho k is greater than 3/4, then we actually further check the length of the direction. Okay, if it reaches the trust region radius, it means that the current trust region radius may restrict the step. In this case, we will enlarge the step length in the following way. Okay, so we enlarge it to the twice. In other cases, we will keep the current trust region radius. Now, coming to the iteration, whether we will jump to the next iteration or not, we have the following ways. So recall that we prescribed a parameter eta before we start the algorithm. So we check whether this ratio is greater than eta. If it is, it means that we can jump to the next iteration. Otherwise, we will keep here and we repeat the process until we find a secondary update iteration. Okay, so this is the trust region algorithms. It runs in the following way. And we have some remarks about the trust region methods. So firstly, it is about the upper bound of the trust region radius, delta hat. So delta hat is the overall upper bound for the trust region radius, and it is usually specified by the real situation. So if you got some preliminary knowledge about this problem as well as the shape of the feasible region, then we can specify this delta hat. Otherwise, we will use the default value. And delta k increases only when we reach the boundary of the trust region. This is what we have specified in the previous page. In this case, it actually means that the trust region may restrict our update. Okay? If we choose a little bit larger trust region, then we may get even bigger progress. Okay? So this is the intuition. Now, the key point of the trust region algorithms is how to solve the subproblem. So the subproblem actually takes the following form. The model function is a quadratic function, and we got a trust region restrictions, meaning that we require the length of this P must be smaller than this given delta, where delta is the trust region radius, okay? So how do we solve this problem? We have mentioned a little bit in chapter 2 actually. However, here we will discuss more details about this subproblem. And in this page, we present the optimality condition for the subproblem. Notice that this subproblem is actually a constraint optimization problem. You got some restrictions on the radius, right? So it belongs to a constraint optimization problem. We will discuss the optimality conditions of constraint optimization problem in chapter 7. Now, in this part, we just provide the result here. We will not give the details of the optimality condition, okay? So, assume that P star is a global optimal solution to the subproblem, and if and only if the P star is a feasible point, meanwhile, we can find a scalar lambda which is non-negative such that the following conditions are held. The three conditions together are referred to as the first-order optimality conditions, okay? So as you can see, the first one basically says that P star is a solution of a linear system. And the second one is actually, we call it a complementarity condition, which corresponds to the inequality condition here. Okay, you got a P norm smaller than or equal to delta. And finally, this is a positive semi-definite constraints, meaning that we must require this matrix P plus lambda I to be positive semi-definite. So with these three conditions, it is actually, we can guarantee that P star is a global optimal solution. Now, let's take a further look at the complementarity condition here. As we mentioned, this part is referred to as the complementarity condition. So if we take a further detail at this condition, and we discuss two cases. The first case is that if the norm of P star is strictly smaller than the trust region radius. In other words, this part is non-zero one. So in this case, we have that lambda is 0. Then we can directly get the P star to be here. Okay, so P star is actually the Newton's direction. If not, then we can have that this lambda is non-negative. However, we have no further information. So in the second case, it means that we have to design specific algorithms to solve this subproblem. If we are very lucky to get the first case, it actually means that the subproblem of trust region method can be reduced to an unconstrained optimization problem. In this case, the trust region method is coincided with the Newton's method. Okay? Now, let's take a look at different radius have different effects. Okay? So we plot 3 different trust region radius. Meanwhile, we also showed the contours of model function M. If we're looking for the minimum over the smallest trust region for the model function, then we will reach the direction P star 1 here, right? because this is the smallest function value the model function can achieve within the trust region. All right? However, if we enlarge the trust region a little bit, we work in the second trust region, delta 2, then we may reach the direction P star 2 here. Okay? So within the medium trust region radius, we may get an even better step P star 2. And for the largest trust region here, delta 1, you can see that the minimizer of model function P star 3 is already included in this region, right? So we directly jump from the current iteration to the P star 3. Then we get the minimizer of model function. In this case, the subproblem of trust region is actually an unconstrained optimization problem because the trust region restriction will not take effect. Okay, so you can see that different trust region radius may lead to different steps in trust region method. Right, so we stop here and let's make a brief summary about this part. In this part, we introduce the details of trust region algorithms, and we mainly discuss a little bit about how to solve the subproblem, mainly focus on different effects of radius in the trust region method. So we will stop here and see you next time.